Thanks a lot, and it's great to be back in Berlin with all of you, also in this beautiful place. So what I will do, I'll share with you some of the work we're doing at the lab, and then hopefully at the end we also have a few minutes to share ideas and interact. Now, first of all, I want to start with people who try to look at how cities might be in the future. And these are a few images from a number of French artists writing at the end of the 19th century, beginning of the 20th century. And when they were looking at the future, they got a few things right. They saw, for instance, mechanization in farming coming, as you see here. They also imagined at the time, in the early 20th century, Roomba, the little robot cleaning our homes. That's how they thought it would look like. But also they got a few things terribly wrong. So they thought, for instance, I would travel here to see you in Berlin with a whale bus through the ocean, or that the German police might patrol Berlin in this way. And even in your wildest drone fantasies, today you wouldn't imagine this. The point I'm making here is actually a point that was made beautifully by the great Karl Popper, and is about the fact that the future is open, it's not predetermined, and thus it cannot be predicted, except by accident. They got something right and something wrong. The possibilities that lie in the future are infinite. And really what is important, we think at the lab, is to explore those possibilities through design. Design is really the way to look at the city, how it is today, and see how it could be different tomorrow. We are passionate about cities for many reasons, but one reason is what you see on this slide. If you need to remember just 4 numbers about cities, remember the ones you see there, 255, 75, and 80. Cities are only 2% of the surface of the planet. They run 55% of the population, 75% of energy consumption, 80% of CO2 emissions. So if we can do something to make our cities a little bit more sustainable, well, that can be a big deal globally. And what can we do today? Well, Benjamin was saying a moment ago, the digital revolution is really changing a lot of things. It changed a lot of things in our lives. It changed a lot of things during COVID, in the way we work, in the way we meet, in the way we get food, or so on. But it changed a lot of things in cities as a whole. And one way to see this is what you see in this image is that's actually the logo we use at the lab, is the convergence of digital and physical, is a digital twin that's more and more pervasive in our cities. And that means that we can look at cities in a way we couldn't just a few years ago. And that knowledge then can be turned into design, into ideas, into new ways to live the city. That's what we do. We do this at Cambridge, Massachusetts. Also, we got a few labs now around the world, in Amsterdam, in Stockholm, just opened in Dubai. And then we've been working and collaborating with many cities in Germany as well. But the point I'm making is, today we can look at a city like this. We couldn't a few years ago. That's Lisbon, mapped using big data from the mobility network. And again, it's like a living organism. That was done by Pedro Cruz, who was a researcher in our lab at MIT. Now he's a professor at Northeastern University. But again, he shows the city like we couldn't just 10 or 20 years ago. And with that data, we can then look at many different questions. For instance, a couple of years ago, we discovered a new universal law of mobility in cities that can have interesting applications when we plan new cities or we plan new transportation system. Again, we would not have been able, I will not get into the details, we would not have been able to look at this without, in this case, data from tens of millions of movements, anonymized movements from people around the world, and analyzing that to really see the regularity, the universal regularities of those movements. Or another little story is about something that bothered me since I was a PhD student at Cambridge. When I was a PhD student at Cambridge, I was in that college called Darwin College, and I realized something very strange. I was going from the college to the department, following one route, call it Route A, and I was going from the department to the college, back to the college, following a different route, Route B. And that was consistent. So it was consistently inconsistent. And I mean inconsistent because if you look at shortest path, the shortest path is the same. A to B should be the same as B to A. If you go from here to whatever, Potsdamer Platz, if you take the shortest path, should be the same if you go from here to there or in reverse. If you're walking, or if there's no one-way streets and so on. And that bothered me because I say, what is it? Well, it's only my brain or is something that's more general? And just last year, we managed to solve that question, again, looking at a lot of big data from cities. There's a paper. I show the papers so that if anybody would like to download them, all of them are on our website at MIT. But basically what we did, we looked at hundreds of thousands of people, how we move in Boston and in San Francisco. And it turns out our brain doesn't follow shortest path, which is interesting because we are working more and more with phones that optimize in a different way. You know, if you look at your maps, they do shortest path, but our brain does something different. Something that people have been studying with animals called vector-based navigation. You follow a vector. Or another way to say that is that you're minimizing the angular deviation versus your objective. And if you look at that, the difference between the two is that, you know, it's not the shortest path, it's close enough. And probably from an evolutionary point of view, if you think about our ancestors thousands of years ago, when they had, you know, that's a good way to get something good enough, but to save some brain power to look at other things. It's much easier to compute than if we had to do the actual shortest path. But, you know, it gets us to the destination, it's good enough, and we can still pay attention, maybe a few thousand years ago in the savannah, about a tiger, a lion, or some other things along the way. So again, you know, data can help us to understand the city, but also to reprogram the city. In this case, we started from very simple data. What you see here, every dot is a taxi pickup and a taxi drop-off. A yellow is a pickup, a blue is a drop-off. This is New York. Which place is this in New York? Any thoughts? Yeah, sorry? Not Times Square? No? But I think I heard JFK. I think, yes, it's JFK Airport. So they said, yeah, if you landed in New York, you know, those are some of the terminals. If you zoom out, you see JFK is down there. And you see all the other points. By the way, a couple of things. If you look at the map carefully, in that map, there's no roads, but the roads just emerge because of the sheer number of pickups and drop-offs. So, you know, the map is totally black. You only see in gray the water, but actually just emerges. And by the way, that was done by Benedict Gross, who's now has been operating in different parts of Germany, including Berlin. He was at the lab for a year with us, and he did this, some of this beautiful visualization work. But then we got the data. The data was made accessible. This was a few years ago, before Uber launched Uber Pool. Data was made accessible by Mike Bloomberg, at the time the mayor of New York. And the first question we asked ourselves was the following. If you look at those 2 points in Manhattan, between them, in the course of the year, you got hundreds of thousands of trips. It means some days you got over 1,000 trips connecting point A to point B. And so the question is, you know, well, how many of those trips could be shared by two people going more or less in the same direction? How many taxis we could share? And the inspiration, again, was something I think I experienced many times, I'm sure many of you as well. You are in New York, you are at a hotel, you're going to the airport, you're there with your trolley in the morning. Next to you, there's somebody else, another trolley. And you know, you're going to the same place, you could have shared a ride, but you didn't know it. It happened to me last night at Tegel as well when I landed. So how to quantify that? Well, when you got big data, sometimes you need big math or new mathematics. So if you try to solve that problem of shareability using traditional mathematics, especially linear programming, it simply fails because there's too much data. So we look at a new approach based on network science. We call this shareability networks. You see them here in more detail. If you're interested in the math, is the previous paper again. And what we discovered actually was interesting. In New York, you could take everybody to destination when they need to be there with a very small delay. Is what you see there on the x-axis, upper left graph. The maximum delay, you know, 1, 2, or 3 minutes. That's in seconds. But then actually with a huge amount of shareable trips. So you could take everybody to destinations, I was saying, within very small delay, 1, 2, or 3 minutes, with 40% less vehicles than what we have today. The interesting thing is that when we developed this, Uber had not launched Uber Pool or Uber Share yet. There was a nice discussion in New York. A lot of people started talking about the project. I remember the New York Times did a review of this paper, and the editor, Nick Fox, he wrote, you know, well, you know, this is an interesting piece of mathematics, but, you know, New Yorkers really don't want to share anything. It turns out that's not the case, because after this, Uber reached out. We did a first collaboration between Uber and MIT. And as you might know, now, Uber and many other companies are offering similar services of sharing mobility all over the world. So it has become, there was a pause during COVID because of the risk of contagion, but now it has become a very significant industry globally. And for us, it's nice because every time you pull a trip, it means one less car on the road, which means less energy consumption, less pollution, and less traffic overall in our cities. So again, using data, we can really understand the city in a different way and try to program it. Remember at the beginning when I was saying about design? Well, these are very mathematical papers, but I see them as design papers. They look not at how the city is, but they look at how the city could be different. In this other project, this was in Nature a couple of years ago, we looked at another problem, which is what is the minimum fleet you need to keep Berlin or Manhattan on the move? No sharing, but just better intelligence. That's again the real data from New York. And today, a lot of if you look at the taxis, they're empty half of the time. They're just moving around, waiting for somebody. So if you optimize that, it's what we call, again, the minimum fleet problem. Then you get something quite interesting. And you'll see it in a moment. Here is how the algorithm works. So you can prove mathematically that's the absolute optimum. But then what you see is that you can, quote, run the city, not with over 8,000 taxis, but with a little over 5,000. And tomorrow with self-driving, this could go even further. So if you got a system based on self-driving mobility, you could really cut a lot of inefficiencies and have 50% of the vehicles we would need today to run the city. So again, the fact that data can help us to understand the city and eventually change it and program it in a different way. Those are the papers, if anybody is interested. But today I wanted to share, a bit more about different type of flows. This another type of flow is not only moving people, it's about moving goods. And one of the things that always bothered us is if you look at that computer there on the table, today you know everything about it. So every chip in the computer, you know where it was produced, how it moved on the planet, how it was assembled, how it became the machine. You also know how that got to your desk. You can trace all of it. Now, you use it for a few years. At one point, you stop using it, you sell it. Somebody will throw it away then, and then you don't know anything. There's a big asymmetry between everything we know about how things are made and what we don't know today about what happens to things when they become waste. And so our idea was, how can we understand that better? How can we avoid what sometimes happens? That a lot of waste, especially e-waste, ends up in places such as this one. And so our idea was quite simple, was what about if we design a little tag to put on trash to follow trash? We had to design it. It's almost like a miniature cell phone. The difference is that your cell phone needs to transmit a lot of information for a very short amount of time. So one day, 2 days, or whatever, but you transmit a lot of data. In this case, you need to transmit very, very little data, so just locations, say, but for a very long time, for months or even years. So we designed this kind of miniature cell phone. We did a first deployment in the city of Seattle. Here it is. 500 people came with 3,000 pieces of rubbish. We put a tag on all of them, anything from banana peels to e-waste, electronics. And after tagging all of them, we started following them. So here you see 3,000 objects, the day of deployment. After a few days, you see some of the landfills next to Seattle. But actually a big surprise, how far stuff started to travel. Sometimes in crazy, unpredictable ways. Look at the trace went all the way to Chicago, changed its mind, and went back to California. And it's still moving after 1 month or 2 months. We thought the Farewell Symphony was the right music here. So we did this project quite a few years ago. Now we're still working actually on all of this, so I will not show you the latest work is in progress, but really seeing still how we can learn more about things when we throw them away. Because obviously the goal is tomorrow to minimize everything related to the linear economy and be more and more circular. And again, technology and data are probably one way we can do that better tomorrow. And I'll tell you more. I'm just not showing some of that, but it's because we are still working on it. But that's one of the main focuses we have at the lab. Now, still about flows, I want to share with you something about mobility. Still, this is the city of Amsterdam, and the mayor of Amsterdam came to us a few years ago and wanted us to work a lot on autonomous driving. As you know, everybody is thinking today about autonomous driving, self-driving cars. When you got a self-driving car, a lot of dynamics in the city can change. And so many cities are interested in this. Plus, we had been working, this was 5 years ago, we had been working with Singapore already for a few years on self-driving mobility. Singapore wants to be the first city in the world to be totally self-driving. And so we started working with Amsterdam. But if you look at Amsterdam, the beauty of Amsterdam in the center is that you don't have much asphalt, but you got a lot of canals. And so we started thinking about, well, let's not think about self-driving cars, but what about self-driving boats? We call them robots. Well, what can you do with a robot? You could use it to move things around. You can use it to move people around. You can use it to monitor air quality, water quality. Or you could use it like an infrastructure to create a dynamic architecture. Think about a temporary bridge when you need it. Think about a floating stage. Think about some dynamic responsive architecture based on the needs of the city, for emergency, for a concert, for something special. By the way, is nothing new. It's what the city of Venice has been doing for a very long time. There's during a very specific day called the Festa del Redentore, when all the gondolas come together and do a temporary bridge. And I think what I like about technology is that sometimes technology is not a way to create new needs, but it's a way to look at old needs and just do what we always wanted to do, but do it in a better or in a different way. And by the way, that's said in a beautiful way by Paul Valéry, the great French writer. He says, what I want from a modern life is actually the ability to lead a non-modern life in a more comfortable way. So I'll show you briefly how we did it. We started 5 years ago. These were the first models, different type of propulsion. We used water jets and something else. This was a 1 to 4 scale, so very, very small. Tested in Amsterdam here. You see it's very controllable, symmetrical. You can move left and right. You can also move laterally, as you'll see in a moment. This was probably 3 years ago on the canals. You see, it moves laterally. We told the mayor, no worries, even if the research fails, we'll open a toy company, because everybody seems to have so much fun playing with this in the canals in Amsterdam. And to do that, we had to look at all the data again, to look and monitor, map all of the flows in the canals. That was quite a research project in the research project. The robot looks at a LiDAR, a 3D scan to move. And so here is actually how a robot sees the city, which is interesting in itself, because you learn a lot about the city that then you can use for something else, for the stability of the sides of the canals, for the buildings. But that's how a machine, a self-driving car or a self-driving boat, looks at the city. Every second, 300,000 points with a very high accuracy, a few millimeters. And little by little, you got this incredible, 3D model of the whole city. And then when you got all the data, you use it in order to teach the system how to drive with artificial intelligence. There's a small, what happened, sorry. That's a small test in, this is an MIT swimming pool. To Benjamin, that's what at MIT we use the swimming pool for, to test these things. You'll see now how it avoids obstacles, different types of obstacles. He's actually Wei, our postdoc. He got promoted after this. And you see, you got all the data and the system learns, you use deep learning and other systems in order to teach it how to avoid obstacles and how to drive. There's some of the papers online you can find on our website, and this is how it is today in Amsterdam.
This is Lucy. Lucy is a rowboat, a fully autonomous, zero-emission boat that operates on urban waterways, and she can change the way cities work. As congestion and emissions continue to rise, while cities continue to grow, the existing infrastructure of many cities struggles to keep up. Rowboats offer a solution by moving road traffic to the water. By bringing passengers from A to B, or as an on-demand boat, taking you anywhere you want. And they can also help the city as a multi-purpose workboat. Take Crystal. She is equipped to collect household waste to free the streets from heavy garbage trucks. Rowboats are fully autonomous, so they navigate without a skipper and can operate 24/7. In order to sail by themselves, rowboats need to perceive their environment and recognize objects such as bridge pillars, floating objects, and of course other vessels. The primary source of information comes from a LiDAR sensor, but rowboats are also equipped with cameras, GPS, and a digital compass. Rowboat's onboard computer combines and processes all of the data and runs the rowboat software so it can successfully complete its mission plan. After 5 years of development, testing and experimentation, we have now successfully enabled autonomy on the full-scale prototypes. Rowboat is ready for the next step. Join us and let's unlock the potential of urban waterways together.
And as we often do with many projects from the lab, this also led to a startup. And actually, the first robots will be presented next year at the opening of the Paris Olympics, tested on the river and be used by people commercially. I wanted to finish with an important thing. I think I was telling you today I focused just on flows, but it's something vital for our city is actually about the flows of energy. And so I wanted to share with you briefly a project we did in Helsinki. This is done not by MIT, it's done by our design office. But the city of Helsinki launched a big challenge called the Energy Challenge to find a new way to do district heating in a more sustainable way. As you know, district heating is usually very good. You produce power, and as a byproduct, you got hot water that you run to heat the city. But the problem in Helsinki is that the power is generated today mostly with coal power plants. So the mayor ran a competition a couple of years ago, open competition, decided something quite brave, like an X Prize in the United States, to put a prize and let people compete from around the world for solutions. Over 250 participants, including big companies like the energy company from China and so on. 10 finalists, and then the winners announced again around 2 years ago. And including our team. I'll show you briefly just the idea we developed. First of all, this was done, as I said, not from MIT, from our design office in New York, but also combining many different engineering teams. Very proud of 2 German engineering firms we really love. We work with them a lot. TransSolar, probably the #1 engineers for climate engineering, based in Germany and then all over the world. And also SBP, the company started by the great Jörg Schleich, was a friend who passed away, I think, a couple of years ago. A great engineer. He's the engineer who did, for instance, the beautiful structure with Frei Otto for the Munich Olympics, and some of the most beautiful lightweight structure in the 20th century. So with them and also some big companies like Danfoss, Schneider Electric, and so on. I just want to share with you the video, but that's to say, out of all the flows, we looked at flows of people, flows, the movement of vehicles, the movement of waste, but clearly the flows of energy are going to be the crucial thing defining our cities tomorrow if we are serious about decarbonizing and meeting the targets we've all set. So just a little video, and then we'll have a couple of minutes for Q&A. We're excited to present to you the Hot Heart, an innovative solution to decarbonize Helsinki. Here is how we do it. Thank you. I finish here.
So we have time for one or two questions, if there are any.
Ideas, comments, criticism. Yes. Thank you. I don't think it's working. Is it working?
Is it?
Now, yes. Yes.
Thank you very much for your talk. Could you explain how the hot heart works?
Yes. So, and the idea is very simple. I'll tell you. So, let me tell you in a nutshell. So, the problem today, renewables are very cheap. If you look at producing 1 megawatt, take the key unit of energy, 1 megawatt hour. 1 megawatt hour of power, if you produce it with renewables today, will cost you in Germany, I think, around 20, 25 euros. If you do it with wind, if you produce it in Italy with sun, it's 20. In some parts of the world, it's actually closer to 10. 10 euros per megawatt hour. That's really nothing. It's super cheap. But the problem is, we all know for renewables, is how you do storage. And storage today is still super expensive. So 1 megawatt hour, remember, on average, whatever, think about 20 euros. But the battery to store 1 megawatt hour will cost you today 200,000 euros. And that price is not going to go down easily. You've got lithium, you've got all the mining to do and so on. So that price is still very high. So again, 20 euros to produce, 200,000 to store it. And then in Helsinki, so the idea was something that if you are an engineer, you would say this is a thermodynamic crime. But it makes sense here. Why is it a thermodynamic crime? Because usually, clearly, power, electricity is a higher form of energy. You can do a lot of things with electricity that you cannot do just with thermal energy. But hey, in Helsinki, ultimately, the goal is to heat the city. And so our idea was, instead of storing electricity, why don't we store just hot water? And if you think about storing hot water in a lake, think about the lakes in Berlin or in Helsinki, in the Bay of Helsinki, it's very simple. You just have a floating reservoir, like the one we did. I didn't go into the detail. Together with Jörg Schleich's office, we designed them in a structure similar to a bicycle wheel, so super light. And then when you do that, the cost to store 1 megawatt hour, in that case, not as electricity, but as thermal energy, so you can call this like a thermal battery, the cost is not anymore 200,000 per megawatt hour, it's closer to $200 per megawatt hour. And then everything changes. So when you do it, everything changes, and then when you got these kind of floating reservoirs, you can also do a nice experience on the top. That's why we thought we use the top. Some people were saying, why don't we build the condominiums on the top? And we say, well, let's build a public space for people to learn about the energy transition, to learn about decarbonization, and so on. And that's how we created this kind of hot body of water and this kind of biome. So that's in a nutshell. Sorry if it wasn't too clear from the video. I'd love to discuss it in more detail. Today we didn't have too much time, but thanks for the question. Yes? You can also shout.
You showed a lot of ideas for mobility.
Yeah.
Do you have one policy recommendation to form that into a strategy how to decarbonize mobility?
Yeah, I got two suggestions. The first one is we should try many things and see what works or doesn't work. Sometimes cities are too conservative. They just want to find the right solution. Well, I think we need to do something more similar to what venture capital does. If you look at how startups are developed, you try 100 things, 99 will fail sooner or later, but one can be a world-changing idea. So I think my first suggestion would be for cities in terms of policy, let more experimentation happen, let more almost like a startup ecosystem happen in mobility and other things, and then, use the city as a lab and see what works, what doesn't work. That would be the first thing. The second thing is also, let's make sure there's not disincentive like we have today. We are subsidizing still fossil fuels in different ways. So let's make sure that the incentives will lead us to more decarbonization. Those would be my two very quick policy recommendations. Yes?
Thank you. I'm wondering about the process.
Use the mic maybe so people, yeah.
Thanks so much. Regarding the robot,
Yeah.
could you speak a bit about the challenges maybe in working together with the municipal government and about the reactions that the citizens showed when they saw it?
Great question. So first of all, in Amsterdam, we've been working with the municipal government, and we think that's very important. If you just do research in a lab in a university, then a lot of that is lost. You do beautiful papers, publish in good journals, you advance your academic career. But if you want impact in the cities, it's very important to team up with the government. So it has been great to work with the mayor's office in Amsterdam, and the same we are doing in Stockholm, in Dubai, in Singapore. In the places where we got a base, we try really to have a good relationship with the local government. Sometimes they are the one funding our research, like in Amsterdam, sometimes not. But it's very important in order to do that the transfer. So that's a key thing. About the people in Amsterdam was not such a big deal, and I'll tell you why. Because the boat is, by the way, I'll tell you a couple of things. When you look at self-driving, at autonomous cars, you got usually 5 levels. The maximum level is called level 5. Now, level 5 means you are in Berlin, you got an address in Munich, in Marienplatz in Munich, and then you press a button and the car should be able to take you from here to that destination with you sleeping and doing something else. So everything done by that. That is still quite a few years away for cars. But the 2 key parameters for being level 5, so total autonomy, the highest level of autonomy, the 2 key parameters you can imagine are very similar to the one that would happen to a person, to a driver, to a human driver, which are the speed. The faster you go, the more difficult it is, and the complexity of the environment. If you're driving on an American highway, it's quite easy. If you're driving in the middle of Cairo, it's more difficult. So complexity and speed. Now, with the boats are very limited, so the speed is very low, and the canals are quite simple to study. So in the boats, we actually managed to get to basically level 5. Today, you could say they're basically level 5. And so because of that, I think people also jump on that more easily. In Singapore, we've been working, I didn't show it, with the government on self-driving cars. It was very interesting. We had to bring a lot of people. We did a lot of experiments. We brought thousands of people to try the self-driving cars in order to make sure people would understand the challenges, the technology, what works, what doesn't work, and so on. But somehow in Amsterdam it was easier because lower speed, simpler environment, and people were ready to jump on the boat, are ready to jump on the boat. Next time any of you is in Amsterdam, send me an email and I'll organize a tour.
Thanks so much. I'm afraid we're out of time, but Professor Ratti might be around for a bit longer. So thanks again,
Good.
Professor Carlo Ratti, for your talk.
Thanks a lot. Thank you.